Hello guys, welcome back to one more video session. In this session, we'll be discussing about the types of linkages. There are two types of linkage. One is if the two genes on the same chromosomes are very closely associated or situated, then obviously it is actually tightly linked genes. Two genes will be tightly linked. So that is complete linkage. Whereas if the two different genes present on the same chromosome, if they are situated far away from each other, there is a distance, we could see quite a distance will be seen between the two different genes, then it is called as incomplete linkage. The basic thing to understand is when a complete linkage happens between two different genes on the same chromosome, obviously what you see is more parental type, less recombinants, correct? Okay, whereas in this case, more recombinants, less parental type will be seen in incomplete linkage. To explain this, I will draw one chromosome. Okay, so this is a chromosome. Okay, let us just put as many genes as possible in this chromosome so that you can easily understand the distance between the genes, or you can easily understand what is complete linkage or incomplete linkage. Okay, so here we just this is the locus of gene A. Okay, and just below it there is another gene. I am using blue color here, that is gene B. Okay, that means very minimal distance is present between A gene and B gene, correct? Okay, so again here the another locus you see gene C. Okay, and now here you see gene D. Okay, and here you see gene E, and again I am using blue color. Okay, very close to gene E's locus there is another gene which is F. Okay, so that is fine actually. So how many genes are there? Total 6 genes are there present on the same chromosome. What is linkage now? Okay, so linkage is nothing but when exactly on the same chromosome, if you see many genes are present for different characters, then it is called as linkage. Okay, so there are two types of linkage. As I said, complete linkage is very simple. So during the crossing over, for example, if I draw another chromosome, okay, so this is another chromosome. Hope you can see this. Okay, in this case I will use only white color, so it will take a little time actually if I change the colors. Okay, now let us assume that there is a small a, and just below that there is capital B. See, dominant B is there, and here let us assume that small c is there. Okay, obviously gene means they always occur in pairs, because on homologous chromosome obviously they also occur in pairs actually. Okay, here let me just write small d. That means for capital D, small d is there, so that means obviously capital D if goes to the gamete, then the progeny will have a dominant trait. Okay, so if a small d goes, then obviously it will be recessive trait. That's it. Okay, so in this case I will write that is homozygous EE, and below that there is F, that is also capital F. Both are dominant. Okay, doesn't matter actually, it's very easy. Okay, here, so during actually that when the meiosis takes place, what happens actually? That in females it is very convenient to explain. In females, if you take all the chromosomes have its pairs, that is homologous pair is present, correct? So total 23 are there. When it compared to males, obviously you see when it comes to the last sex chromosome, the allosomes, one X is there, along with that one Y is there. That means actually it is hemizygous condition. For X, for whatever the genes which is present on X doesn't have its another pair. Pair is completely absent. Why? Obviously because there is no X chromosome. Even it is comparable for Y also, where Y also lacks its partner genes, correct? Okay, so this is very important. Okay, so you have to remember this particular concept of statement when I talk about linkage groups. Okay, fine. So now during the meiosis, what happens in the female? As I said, like it is convenient to explain. In the females, all its homologous chromosome they come. For example, there is one chromosome, for it there is another homologous chromosome. Okay, they come very close. What is it? Synaptonomal complex occurs. During that period, actually the chromatids of each pair or each chromosome actually they just swap in the sense like they touch each other. This is called as the crossing over. During the crossing over, what happens? Whatever the genes which is present, we don't know like which segment of the chromosome is actually undergoing swapping or crossing over. Okay, we don't know. Let us assume that in this segment. Okay, this segment now. So for example, if I use a pink color for this segment, okay, So obviously here we use white color. Okay. So here small a and capital B is gene is there. Okay. During swapping, let us assume that this particular piece of the chromosome now transferred to this particular piece of the chromosome, and the pink piece of the chromosome goes to this. That means, so during the crossing over, this piece will now transfer to this chromosome. Let us name it 1 and 2. Both are actually homologous chromosome. And this one, the white color one piece earlier I used, okay, will go to this chromosome. So when it actually undergoes crossing over, what will happen? See here, the A and B cannot be separated because the space is minimum. Okay, it cannot be like cut between A and B. There is no gap actually between it. Obviously, when actually entire piece shifts, AB also goes along with the piece, and as a result, what you see is, you see both capital A and capital B is present. But what is the difference you see? See here, one gene which is actually earlier was recessive, now it is shifted to this piece or this chromosomal piece. Obviously, what happened, or segment? So here it gets capital A. What happens to this? It becomes small a because it gets small a from this chromosome. And here the capital B itself, but the gene which was present here now comes to this segment of the chromosome. That's it. But here actually both are in now dominant stage, nothing will happen. But which is affected? This is affected because earlier it was capital A, but now it becomes small a. This is actually crossing over. Okay, so what is complete linkage? This is a very good example for complete linkage. That means actually during the crossing over, the two genes will shift to another chromosome. They will shift actually because it cannot be separated. It can't be separated. When two different genes are situated very close to each other during crossing over, it cannot be separated. If crossing over happens, obviously both the genes, that is examples like capital A, capital B genes will shift to another homologous pair. Whereas if in the other pair, if small a and capital B is there, that will shift to this chromosome. That is actually shown there. Okay, so that is the complete linkage. Okay. Why complete linkage happens? See here, both the genes, like let us say in this case E and F, where they are tightly linked. When the two different genes are tightly linked, obviously that show complete linkage. Okay, remember it. I will just write tightly linked. Okay, this kind of complete linkage is seen very rarely in nature. Very rarely in nature. You don't see them often. Okay, some examples. Please note it down. Male Drosophila. In male Drosophila, the crossing over never takes place, particularly in its allosome. You know why? Simple. The reason is, when it comes to the allosomes, where the X lacks its partner, where Y lacks its partner. That's it. That is the reason why the crossing over doesn't take place in male Drosophila. Please remember it. You may get a question. Give an example for complete linkage. Male Drosophila, you can just write what that means. Please understand, complete linkage means if the crossing over happens, both the genes which are tightly linked will shift to another chromosome, that is homologous chromosome. Otherwise, the crossing over doesn't take place because it's a complex mechanism where the two genes shifting is not allowed. Okay, it's not good actually, so it is not allowed. If it happens, obviously both the genes will go. It's like buy one get one free, like that. Okay, so and another one is in the case of female. Bombyx mori, silkworm moth. Bombyx mori, in this organism, in the particularly female one, you see no crossing over. What is the reason behind it? Because in the Bombyx mori, the sex of the offspring is determined by the female. Okay, I think it is female heterogamety in this case. It will be like this, ZO0 actually. I will tell you, we will talk about it. Matlab in the allosomes, Z lacks its partner, where O in the sense nothing. There is no chromosome. Okay, like that. Okay, so please remember this. We can actually take one example for complete linkage. Let us see what is the phenotypic ratio. Okay, phenotypic ratio and genotypic ratio of this complete linkage. Let me just write it. The phenotypic ratio of the complete linkage will be 3:1, whereas genotypic ratio will be 1:2:1. If you do the test cross ratio will be 1:1. Let us see how. Okay, so for this, I will explain incomplete linkage after if I have some space. Okay, after explaining. Otherwise, I will erase it and explain. What we do is we take a simple example. I am not explaining this. I'm explaining complete linkage. Okay, so what we do is we take two chromosomes. Now, to make you understand it, I'm not going on sex linked inheritance. I will take the autosomal inheritance, that is actually the chromosomes of, that is autosomes. Okay, I'll be the structure determining chromosomes, that is except allosomes, whatever it is there, that is autosomes. Okay, so so we use white color here, doesn't matter actually. Let us just assume that here there is a gene which is capital A, and very close to capital A gene there is another gene which is actually capital B. And here also we write capital A and capital B. That means actually these genes are homozygous, AB, capital AB, capital AB. Okay, a cross with another organism with the chromosome, same chromosome, but it is, in this case, it is having genes, all the genes are recessive, correct? Okay, now what you have to understand is, here actually the gap is very less between the two genes. Obviously it shows complete linkage because the genes are tightly linked. So whenever crossing over happens, if it happens, okay, that means the crossing over, AB gene will shift, that is actually it acts like a one unit. So that means actually, you know, when A gene goes, obviously B gene also goes. If B gene is selected, A also selected, like that. So it acts like one unit. Remember it? Okay. That means please remember, in complete linkage, if crossing over happens, then the two genes acts like one unit. It acts like one unit. Okay. It looks like only one gene, but there are two genes because you can't see the other gene because it is tightly linked actually. So here also one unit. Now to make you understand it, I am going to just use this one unit, that is AB as capital letter P. Okay, capital letter P, and in this case here also I use capital letter P. That means actually the gene, we can actually write this as capital P, capital P. Correct. We can write this as capital P, capital P. We take it as male. Okay, E is crossed with this. This also acts like one unit. Let us take it as small q, and here also we take small q. Okay, so in this case what will happen? We just write it as Q. Okay, so now let us see offspring, which is F1. Okay, so we'll not take the gametes, obviously we know it. Okay, so it will be this. The F1 progeny will be PQ. That means it is understood that A, small a, capital B, small b. That is actually in heterozygous condition. That is nothing but dihybrid cross actually. But to avoid like it consumes a lot of place, so we just take E, capital AB as capital P, small q as small a b. That's it. Okay. So now again you know the rules. Okay, like this, you know it. That is nothing but selfing. In this case, okay, we just do it directly. Okay, the cross between, let us take it as male, and this is as actually female, capital P, small q. Okay, so now capital P, small q, then capital P, small q, then small q. This is actually what we got in F2 generation, correct? Okay, now as I said, what is the genotypic ratio? I have already written like genotypic ratio is 1:2:1, correct? Here you could see this is 1. Okay, these are actually PQ, that is 2. Then this is QQ, that is actually 1. So remember, for a complete linkage it is 1:2:1 is the genotypic ratio, whereas the phenotypic ratio is, I think you can easily, okay, so this is 1, this is actually sorry, when capital P is there, obviously it is dominant or it will suppress the small q, that is recessive. Obviously 3 phenotypes will be obtained and 1, that is recessive phenotype, will be obtained, that is 3:1. Okay, it looks like Mendelian's monohybrid cross. No. Okay, fine, hope you understood. Okay, so that's it. If you want to do the test cross, okay, as I said, like test cross ratio is 1:1. What we do is, I think you can see this. What we do is we have P and small q, which is crossed with its recessive parent, that is small q, that is nothing but small ab, correct? Okay, so I think if you do it, you will get 1:1. I think you can do it. Okay, so okay, fine, we'll do it. P here and Q here, PQ, QQ. That's actually the thing. So 1:1. That's actually the test cross ratio. Now I'll explain about the incomplete linkage. So I will erase it. We'll see incomplete linkage. I write incomplete linkage. So So you know that when incomplete linkage is seen in a particular chromosome, that is actually the greater the distance between two different genes on the same chromosome, obviously there is a high chance of getting recombinants, that is getting non-parental type. That is actually we have seen in T.H. Morgan's second Drosophila experiment. Hope you remember it. That is actually, you know, what is it? The color, that is actually eye color, that is small w, which is situated on particular chromosome. Let us just write it here. This one, okay, that is exactly on not particular X chromosome, okay, small w. And whereas, you know, another character, that is miniature wing. See here, there is a gap, a greater gap between small w and small m. Okay, this is for the eye color, white color, and this is for the miniature wing. If you take the dominant rate of it, obviously you can make out here, correct, w plus m plus, that's it. This is very, very important. That means Morgan identified that the gene which is responsible for the shape of the wing is actually situated away from this w plus w, or even actually another one, that is y plus also even. So that means w plus and y plus exhibit complete linkage. Okay, that means, you know, you are getting parental type. It is more, we have found it in cross 1, that is 98% parental type. In this case it is actually y. Okay, that is also shown parental type. But when he crossed by taking two characters, that is actually the eye color with the wing size, that is obviously we got more non parental type, that is recombinants. That's very important. Please remember it. You may get a question actually. The situation, the position of genes w plus y plus closely linked, whereas w plus m plus away. Okay, it is also applicable to this also, the recessive form also. Please remember it. Even y plus m plus is also in good, I mean, the distance is greater between the two genes. Okay, incomplete linkage obviously occurs normally. It's very, very commonly seen. That's what actually we need variation, right? Okay, so it is very, very common. And one more thing is, if I draw the chromosome, let us take it as X chromosome. We'll take one character that is actually same, W plus, and very close to it, what is it? Y plus is there. Somewhere else here, what is there? Actually, M plus is there. That is for wing size. Okay, what you see is the distance. You see the distance actually. Okay, this distance is actually also called as centimorgan. The distance between two genes on the same chromosome is called as centimorgan. We'll write here centimorgan. Okay, centimorgan. So normally, see here, how to calculate centimorgan? Okay, we'll do it later actually. Okay, centimorgan is the unit which is used only for the distance between two different genes, only which is if it is present on eukaryotic chromosome. Remember it, centimorgan is the unit which is used only for measuring the distance between eukaryotic genes, two different eukaryotic genes present on the same chromosome. Remember it, as for eukaryotes. And again, actually, you know, the map unit is another unit which is also like called, that is nothing but centimorgan itself, but this particular term is used only for prokaryotic chromosomes. Remember, map unit for prokaryotes, that is bacteria, whereas centimorgan is for us, that is eukaryotes. Both are same actually. What is centimorgan? That is the distance between two different genes actually on the same chromosome. That is centimorgan actually. There are so many problems you get for NEET, particularly on centimorgan. You have to calculate. It is also called as the gene map. What is gene map? The distance between two different genes on the same chromosome. Okay, gene map. Okay, so that's it. I forgot to tell you one more thing, that you know the gene map was discovered by the student of T.H. Morgan. We'll write his name here, Alfred Stewart Went. Okay, I think E is there between a T and V. Forget. Oh, it's fine actually. Alfred Stewart Went actually discovered gene map. It is also called as chromosomal map. Chromosomal map. Chromosomal map. Just remember it actually. So that is the distance between two different genes. Okay. So here we just write more the distance between genes. More the distance between genes. I'm talking about W plus and M plus, two genes, different genes. More the distance. So here we just write distance between the two genes is directly proportional to the crossing over. That means the crossing over happens if the distance is more greater between two different genes. Actually, correct, right? You can easily think about it. See here. If imagine another chromosome is here, if it comes very close to this one, obviously, like we can easily cut. So we can easily cut the segment here. That means actually the W plus can go to another one, whereas if it is heterozygous, if W is there, only W is there, that is recessive gene, can come to here. That means actually it will change the entire zygosity of the genes. Correct? Hope you understood this. Okay, so distance between the two genes is directly proportional to the crossing over. It happens actually. And more thing is, distance between the genes also directly proportional to the number of recombinants. That means whatever the recombinants you get, obviously in the case of experiment number 2 of Th. Morgan, we got 37.2% of recombinants. Correct? That means the distance between the two genes is nothing but, if you take in the case of centimorgan, that is actually the distance between W plus and M plus. It is, I'll write here, W plus and M plus. The distance between the two genes in the case of experiment number 2, it is 37.2 centimorgan. Correct? That's it. Okay. So what is actually the distance between two genes is nothing but equal to the centimorgan actually. That means if that is also like centimorgan is equal to 1 centimorgan is equal to 1% of recombinants. Can I write like that? Correct? Yes, right? How much I got in experiment number 2? 37.2 centimorgan or recombinants. That is nothing but 37.2 centimorgan itself. Instead of that, we write like that, 37 centimorgan. The greater distance is there. Okay. So for example, if the distance actually between the two genes, let us take it as capital A and small b actually, in heterozygous condition is less, it could be like lesser. Let us take it as 1 centimorgan. Let us just assume that it is 1 centimorgan. So you may get a question like, the distance between A and B is 1 centimorgan. Calculate the percentage of recombinants. Obviously it is 1% recombinants. That's it. Because 1 centimorgan, that's it. Okay, the percentage will be 1 actually. Okay, okay, fine. So now, how to calculate it? Okay, the formula to calculate the percentage of recombinants, calculate the percentage of recombinant is number of recombinants, how many organisms or progenies are recombinants, that is non-parental type, okay, divided by total number of the progenies. That's it. Suppose in let us take it like in 1000, let us just assume that we have 1000 offsprings in F2. Okay, hope I am going fast, I guess. Okay, chalo. I think you can rewind and watch it again. Okay, I got 1000 offsprings in F2. In that, let us assume that 600 are showing parental type. That is actually they are showing complete linkage, correct? Or maybe linkage is seen actually. So parental type is there. Let us assume that 400 are non-parental type, that is recombinants. Okay, now number of recombinants, shall I write here, that is 400. What is the total number of progeny? That is actually 1000 into 100. That is actually the form. Oh, I didn't write 100 here, because to calculate percentage we have to, correct? Okay, so now actually you can do it. So the okay, so the percentage is 40, correct? Okay. Remember one thing, the percentage or the frequency, I think I'll write F, frequency of recombination is also called as crossover value. Can you write like this? Frequency of recombination is also called as crossover value. That is nothing but you have to use the formula, and ultimately it should be less or equal to 50%. Always remember it. It could be less, it should not exceed more than 50%. See here, we got 40%. Okay, and it could be equal to 50%, but it should not exceed more than 50%. It should be below 50% or could be equal to 50%. This is very, very important for NEET. Please remember it. Even this also important for NEET. Remember it. Okay, so incomplete linkage is nothing but when the genes are having greater distance, then obviously we get more non-parental type or more recombinants. That's actually the thing. Distance between the gene is nothing but directly proportional to the crossing over. That is also nothing but you get more number of recombinants. That's it. Okay, calculation as I told you earlier. Okay, explained it now itself. Okay, so that's it. Okay, I just forgot to tell you one more thing. That is actually right here. There are two chromosomes. Let us just name it like this: A and here B, and here we write small a, small b. Actually, okay, this is actually homologous chromosome, but the genes are exhibiting heterozygous condition. Correct? Okay. So if the genes are seen like this, then it is called as cis arrangement. Okay, cis arrangement. Okay, so just remember, normally seen in incomplete linkage, cis arrangement, or maybe like sometimes you will see this kind of arrangement, that is A will be remained as it is, whereas small a is also on the same locus, but this B shifts to the locus of capital B and the capital B shifts to the locus of small b during crossing over. Obviously, why? Cis and the trans arrangement happens only when the crossing over happens. When crossing over happens, when there is a distance between two genes. Correct? Okay. So that's it. Okay. So this is actually called as trans arrangement. Okay. That's it. We'll in the next session I'll talk about the linkage groups, and we solve some problems on it. Okay. So because actually, if you solve more problems, obviously you will be confident to solve any different questions actually. Okay, so fine, chalo.